Okay, now we're going to talk about forces in space. Before we start, let's think back. Didn't like that. Let's turn this off. Let's recall that if we have ourself a vector f equal fxi plus fyj plus fzk, that then we can represent the magnitude of that vector. And this probably goes without saying. Everybody gets this. By squaring the components and then taking the square root of everything. So in 3D, let's look at our 3D supports and how our basic supports have changed a bit. They haven't really changed, but let's add the extra dimension to them. So first off, let's go with the roller. So it's a roller like on a 2D surface. So it still is constrained in one direction and will produce a reaction force, just called R. And still we're going to have one unknown there. Say it'll be in the Z direction, and that ball will be free to roll in the X and the Y direction. Now if we pin bearing, if we have a pin bearing again, in 3D, this will now be pinned to the surface, but it will be pinned not just in the X, let's call them R's, and the Y, but also in the Z direction. And this jumps up from 2 to 3 unknowns. And for our fixed case, now we have like a pole stuck in the ground here. And that's going to produce some we'll say Rx, Ry. I don't know. I could really probably be better off drawing these the other direction. Doesn't really matter, actually. Let's keep it Rx, Ry, and Rz. So we have these three constrained here, but this thing also can't rotate about any of these axes. So we'll have a moment at X. We'll have a moment at Z. And we'll have a moment of Y. Now this jumps up to 6 unknowns. So we have here, I just drew a single journal bearing. This thing is free to rotate in the bearing, and it's also free to translate back and forth along one axis. So there's two types. There's this type that's free to rotate. This will produce reactions of an X and a Z reaction, for example, if it's facing this way. It'll be free to rotate and also translate in one. So this will have 4 unknowns. But you can make these in different ways. You can make this square so that it can't rotate anymore, but it can still translate. Or you can make this so it's pinned here and it can't translate, but it can still rotate. So in that case, it would pick up an unknown and move to 5. Now for all these like this, the couple moments here will cancel if you have bearings, multiple bearings. So they're not, you don't have to represent those then in your, so that reduces the number of unknowns. So our equations of equilibrium are pretty much the same. We still can solve the problems scalarly in the same fashion. F of x equals 0, summation of f of y equals 0, summation of fz equals 0, summation of moments about x equals 0, summation of moments about y equals 0, summation of moments about z equals 0. So long as these are all independent equations, you'll have 6 equations, and you can solve up to the 6 unknowns of the fully pinned situation, the fixed situation. But if we're going to do this with vectors, we'll want to think of it like this. Sum of all the forces, vector forces, equals 0. And sum of all our moments about some point O equals 0. So 6 equations for our 6 unknowns. So let's look at this problem. So I have a pole with tension in the B and C and a force pulling down on it like this. And let's draw some axes and such. Let's call this the X direction. Draw that a little better. So Y is this way, Z is this way, and X is this way. So this guy is down in the Z direction a certain distance, and then over in the Y direction. Oops. And that's 30 degrees there. Then this is up 2 meters here. This pole is 6 meters long. And then in the Y direction, this is 3 meters over to here. And it's up the same distance. I think that's good enough for, so let's draw a free body diagram. Here we go. I didn't put units on it, but we can use the picture to the left for the units. But dimensions, I mean. So we have this 400 force. We have the 2 force tensions in force B, force C, and then these are my reactions over here, d, dx, dy, dz. So first things first, let's calculate FB and FC. So we're going to do this with our force vector FB. This is what we're trying to calculate anyways. FB, we're going to multiply this by a position vector and divide it by the magnitude. So this will be multiplying FB by a unit vector, essentially. So B heads off in the -6 direction, -6i. it heads in the -3 direction for y, -3j, and then up 2 in the k direction. That's the direction it is heading. So this is going to be square root of 36 plus 9 plus 4. I squared those terms. That equals 49. So this is going to be 7. So this is just simply -67 FBI minus 37 FBJ plus 27 FBK. All right, let's do FC next. So here we have -6 again, and then up 2. So -6 plus 2, this direction it's heading in, and this results in this vector. Finally, let's set up what F is, and that's going to be 400 sine 30j minus 400 cosine 30k, and that's going to equal 200j minus 346.41k. So we got these vectors all set up here. All these are in terms of FC and FB. Let us now sum moments. I want to sum moments about O, because this eliminates I don't have to take into account my reactions at D. So sum moments at D, really, not O. It looks like an O in my notes, but it's D. Some moments about, I'll make that a really good D, so it stands out. Some moments about D, that's not a really good D. So the moment about D is going to be R from D to A. So it'll be an arm, this arm here, or that'll be my position vector, and it goes to all three of these vectors, so I can just use that same R. So RDA cross B plus RDA cross force in the C plus RDA cross the force. So I can actually do some simplification here. RDA distribution, pull this out, cross FB. So I can just add these vectors, FB plus FC plus F. We'll make that work in the determinant. Well, RDA is just 6I, so there is no J or K component to that. And then let's put these in. So then I'll pull the X components, because we're just adding these all up. So the X components then are the I values, 67 FBI, 6 over square root of 40 FCI, and there is none in here in F. So those are my first term. My second term is just those two J values, and then this is the big term. It has 3 K values, and there we go. So we have a 6 here, and these zeros are going to help us out a lot. So the only terms we have to deal with are these values. Everything else just goes to 0. So if this equals our moment about O and it has to equal 0, then each of our components have to equal 0. So then FB is going to equal 467 newtons. And then I can substitute that back into this J relationship, which also has to be equal to 0. And I can find out what FC equals. And when I substitute back in, I find out that this is 673 and set this equal to 0. Don't forget to multiply that by 6, though. 0.81. This equals, and that's it.